Hey folks, in this lecture we're going to cover the classification of second-order PDEs, and specifically the second-order PDEs with constant coefficients. Now our main goal here is to get to the canonical form of a second-order partial differential equation, and in order to do that we need to understand PDEs a little bit better from the context of linear algebra. In particular, we can think about a partial differential equation as being intimately related with a particular quadratic form associated with our gradient operators. Or put another way, it's going to be a multiplication of the transpose of a gradient operator with a particular matrix with a gradient operator. And using this linear algebra, we're going to have a much better understanding of how linear transformations of our coordinate system affect the partial differential equation. Now that all sounds pretty complicated, so let's start out with a very simple example. Consider the differential equation uxx plus 3uyy minus 2uxy equals 0. I can first rewrite this in an operator form where I've got a partial differential operator acting on my unknown function u. And that partial differential operator is going to be partial x partial squared plus 3 partial y squared minus 2 partial x partial y. So this gives me an equivalent expression for my partial differential equation, but now sort of from the point of view of linear algebra and a linear transformation acting on my function u. Now this operator itself can be written in a compact form using a little bit of linear algebra. Specifically, I can re-express it as the row vector partial x partial y times the matrix 1 minus 2 0 3 times the column vector partial x partial y. And if I do my matrix multiplication correctly, both of the expressions are exactly the same operators. Note that both of these vectors are just the same. The vector on the right hand side is just my usual gradient operator, and the vector on the left hand side is its transpose. So the thing that's really controlling the differential equation itself is the matrix in the middle. As I change the value of the matrix in the middle, I'm going to change my differential equation. So this matrix in the middle is kind of a natural way to encode the information about what the partial differential equation is. When I'm thinking about a partial differential equation, I can think about this matrix, which describes the coefficients of all the partial derivatives. Now, as we know from our linear algebra experience, not all matrices are created equal. And some of the best matrices, especially when it comes to doing things like doing eigenvectors and eigenvalues, are symmetric matrices. So, if at all possible, I want this matrix that I have in the middle here to be a symmetric matrix. And I can make that happen using the following idea. Remember for a second that when we're doing mixed partial derivatives, as long as the function is sufficiently nice, it doesn't matter the order that we do the derivatives. That means that I can think of the derivative with respect to x followed by the derivative with respect to y. That operator is going to be the same as taking the derivative with respect to y followed by the derivative with respect to x. And using this, I can replace this term up here, the 2 partial x partial y, with just a partial x partial y plus a partial y partial x. Those will be the same thing. So my partial differential equation can be rewritten as partial x squared plus 3 partial y squared minus the quantity partial x partial y plus partial y partial x, because that quantity there is exactly the same thing as the 2 partial x partial y from before. But now if I was to re-express this in its matrix form, it would involve a symmetric matrix. Specifically, instead of the matrix 1 minus 2 0 3, I end up with the matrix 1 minus 1 minus 1 3. And from now on, we're always going to write down a matrix that's in symmetric form to represent a partial differential equation. This will mean that either explicitly or implicitly we'll be converting our mixed partial derivatives into an appropriate combination. Let's look at another example. Consider the partial differential equation utt minus 3utx plus uyy minus uxy equals 0. In this case, we have 3 variables rather than our previous example of 2. We can rewrite this in operator form as partial t squared minus 3 partial t partial x plus partial y squared minus partial x partial y, all times u equals 0. And then we can render the matrix version of this, which we want to make symmetric. Also, because there's 3 variables here, we're going to end up with a 3 by 3 matrix. Specifically, it should look like partial t, partial x, partial y, times some 3 by 3 matrix, times partial t, partial x, partial y, all times u equals 0. Now we need to fill in the entries of the matrix so that when we take this product, we end up with the same operator that we did before. When we're choosing the matrix to be symmetric, there's only actually one possibility. For example, when I take this product, this entry here is going to be the coefficient of t squared, which over here is 1. So this entry needs to be a 1. The center entry here is going to be the coefficient of partial x squared. There is no partial x squared above, so this should be a 0. Likewise, the third entry here should be a 1 since it's the coefficient of partial y squared. Now the entries here and here are going to correspond to the mixed partial derivatives between x and t. So we want to fill these guys in with something which is going to add up to the coefficient of partial x partial t over here, which is -3. And we need to do this symmetrically. So we're going to put a -3/2 for both of them. The entries here and here, after I do my matrix multiplication, are going to correspond to the coefficients of the mixed partial derivatives between t and y. And up above there are none of those, so these coefficients here and here should both be 0s. And last but not least, the entries here and here are going to correspond to the coefficient of partial x partial y, which is a -1 in this case. So these should both be -1/2, so that the partial derivatives add up to -1. So if we multiply this out, we'll find out that the operator that I get is exactly the operator from up above. Now more generally, our partial differential equation could have derivatives of order 1, or even derivatives of order 0, which are just constant multiples of our function. For example, consider the rather ponderous example of a partial differential equation here. The key difference from the previous example is that we now feature terms which are not second order in their derivatives, and we need to see how to handle that down as well in terms of the linear algebra. To do this, I'm going to start just as before and convert my partial differential equation into its operator form. And the next thing I want to do is take the part that I recognize with all the second order terms and convert that into the matrix form as I did above. Again, this is going to involve 3 different variables, so I should end up with a 3 by 3 matrix. I would suggest that at this point you might pause the video and try to figure out what the entries of the matrix that I left blank should be. We want to choose them so that the blue term above is going to be the blue term that we're creating now. If it helps, you can actually go term by term. The partial t squared term has a coefficient of 1, and that's what belongs in our first diagonal spot here. The partial x squared term has a coefficient of -1, and that belongs in the middle spot here. The coefficient of partial x partial y is 4, and if I look at my matrix, that's going to correspond to the entries here and here. So both of those should get a 2. The coefficient of partial y squared is a 3, and that's going to correspond to my bottom right entry of my matrix. The -2 is my partial x partial t term, and that's going to give 2 -1s here and here. And last but not least, but the 5 on the partial y partial t corresponds to my upper right and lower left corners, and is going to correspond to 5/2 in each of those. Now for the red part, we're going to write it very similarly, except that it's just going to be the product of a row vector with a column vector. Specifically, we're looking for a vector so that when I multiply it by my gradient vector, partial t, partial x, partial y, I end up with the order 1 terms going here. The order 0 term, -6 in this case, just remains as a -6. So here, because the coefficient of partial x is a -3, my middle term here is going to be a -3. The coefficient of partial y is a 4, So I'm going to have a 4 here. And the coefficient of partial t, well, it doesn't exist, so I'm just going to get a 0. So if I multiply all of this out, I'm going to end up with the same partial differential equation that I started out with. This results in sort of a nice compact way of expressing the general form of a second order PDE. If my variables are x0, x1, x2 through xn, played previously by t, x, y, so on and so forth, then I can express an arbitrary partial differential equation as my row vector of partial derivatives in x times an n plus 1 by n plus 1 matrix A times my column vector of partial derivatives plus some row vector or transpose of a column vector times my column vector of partial derivatives plus some constant all times u equals 0. And any second order homogeneous partial differential equation with constant coefficients can be expressed this way. And the data of the equation itself is going to be encoded in this n by 1 plus n by 1 matrix, this n plus 1 vector, and this constant. We can make this look even cleaner if we adopt our gradient notation. Specifically, if I let nabla just being able to express an arbitrary second-order homogeneous partial differential equation with constant coefficients in such a compact way is already plenty of motivation for adopting this matrix approach and this notation. But it actually gets even better. The reason is that the chain rule has a beautiful expression in this notation as well. Consider a change of coordinates, where I define a new coordinate y0 as a function of x0, x1 through xn, and so on and so forth, ending up with a final variable yn, which is also a function of x0, x1 through xn. The chain rule tells us how derivatives with respect to the new coordinate system relate to derivatives in the old coordinate system. Specifically, I create a matrix which is oftentimes referred to as the Jacobian matrix. The Jacobian matrix is a matrix which encodes all the possible partial derivatives of all of the different functions that are making up our coordinate transformation. So we start at the beginning with the first coordinate function, which defines our y0, and we take its partial derivative with respect to x0, and we also take its partial derivative with respect to x1 all the way through its partial derivative with respect to xn going downwards. In the next column we repeat this procedure for f1, and ending up with the procedure repeated for fn. With this matrix in mind, the chain rule is stated very simply as partial x0, partial x1 through partial xn is equal to j times partial y0, partial y1 through partial yn. So this gives a relationship between the gradient with respect to the gradient operator with respect to the variables x and the gradient operator with respect to the variables in y. Now this is especially nice in the special case of linear transformations. Unlike a more arbitrary coordinate transformation, a linear transformation is itself just described by a matrix. Specifically, y0, y1 through yn are given by some n plus 1 by n plus 1 matrix T times x0, x1 through xn. For this very special kind of transformation, the Jacobian itself turns out to be the same thing as T. Let's see how we can use this to dramatically simplify our partial differential equations. We can start out with an arbitrary partial differential equation, which we write in our most compact form. Our transpose of our gradient operator times A times our gradient operator plus B transpose times our gradient operator plus C all times U equals 0. Now let's think about what a linear transformation of our variables might do to this differential equation. I'm going to use a linear transformation defining y as a transformation of x, which I can write in vector form as y vector equals tx vector. Now, because I've got two different flavors of variables, I've got two different gradient operators as well. So the gradient operator that I started out with for the original partial differential equation is the one with respect to the x variables. So to help me remember this, I'm going to put a sub x on it everywhere. And now I've got a new gradient operator, which will be my upside down triangle or nabla sub y. And what the chain rule tells me is simply that the gradient vector with respect to x is just t times the gradient vector with respect to y. And actually here, I need to correct something. When I said before that for linear transformations, the Jacobian is just the transformation itself, it actually turns out to be the transpose of the transformation matrix. So I should have a transpose here, and it also induces a transpose in the equation down below. Using this, my new partial differential equation becomes T transpose times the gradient operator with respect to y, all transpose times A times T transpose gradient operator plus B transpose times T transpose gradient operator plus C, all times U equals 0. So all I've really done here is replace my gradient with respect to x with T transpose gradient with respect to y. And now I can use a little bit of linear algebra and properties of gradients to simplify this further. Specifically, the transpose of the transpose gives me back the original matrix, but it changes the order of multiplication. And using this fact, my differential equation can be simplified to the gradient with respect to y transpose times T A T transpose times the gradient with respect to y plus T times B vector transpose gradient with respect to y plus C all times U equals 0. And now the beautiful part about this is I have the freedom to choose any T that I want as long as the matrix T has non-zero determinant. It's going to be a non-singular transformation and give me an equivalent partial differential equation. But by selecting T appropriately, I can make it so that the most complicated portion of my differential equation, the matrix portion, is as simple as possible. And the simplest kind of matrix I could think about making is a diagonal matrix. Or even better, a diagonal matrix whose entries are all zeros, ones, and negative ones. And that's exactly what I can do. So first of all, I want to remember that I made the simplifying assumption that my capital A, the matrix that's defining my original partial differential equation, is going to be symmetric. And I can always do that. Give me a partial differential equation and I can put it in a form where A is a symmetric matrix, just by saying that the mixed partial derivatives are going to be the same. And because A is symmetric, we have the spectral theorem, which tells me that A can be diagonalized. Even better, not just diagonalized, but diagonalized by an orthonormal eigenbasis. And if I use those eigenvectors as the entries of a matrix, specifically as the column vectors of some matrix Q, then Q will be an orthogonal matrix, that is, its inverse will be its transpose, and also Q transpose AQ will turn out to be equal to a diagonal matrix, which I'm going to call capital lambda, whose entries on the diagonal are just the eigenvalues associated to the different eigenvectors. So this is the idea of taking a partial differential equation and putting it into what we might consider its canonical or standard form. I'm going to use the fact that that matrix capital A can be diagonalized and use the corresponding matrix Q as the ingredient in my transformation to turn the matrix A into that diagonal matrix. What's more, by rescaling everything, I can make it so that all of my entries are going to be -1, 0, or 1. Specifically, I'm going to define mu k to be the absolute value of lambda k to the -1/2 power if lambda k is non-zero, and 0 if lambda k is equal to 0. I'm going to do that for all the k's. And then I'm going to take my transformation to be the diagonal matrix of all the mu times q. And when I do this, what that means is that TAT transpose is going to be a diagonal matrix, but full of just zeros, ones, and -1s. Here I also need to make sure to take not Q there for T, but Q transpose. And if we multiply this all out, it ends up being that TAT transpose is just the diagonal matrix of the signs of the eigenvalues. Where by the sign, I don't mean the usual sign function, I mean the plus sign or a minus sign or 0. So it gives me 1 if a number is positive, -1 if the number is negative, and 0 if the number is 0. So this means I can always put my partial differential equation into a new form where there are no mixed partial derivatives, and where for all the second derivatives the coefficients are either 1 or -1 or 0, and that's just determined by the signs of the eigenvalues of the original matrix. So it makes sense that the signs of the eigenvalues are what classify the flavor or kind of partial differential equation that we have. So from our study of partial differential equations before, there were 3 main examples. We had the heat equation, the wave equation, and Poisson's equation. Let's look at what each of those guys are in matrix form. For the heat equation, we had UT equals K UXX. Putting it into a matrix form, this is the same thing as gradient vector times the matrix 0, 0, 0, -k times gradient vector plus the vector 1, 0 times the gradient vector all times u equals 0. And again, it's the eigenvalues of the matrix which matter. So looking at this, the eigenvalues are going to be 0 and -k. For Laplace's equation, we have uxx plus uyy equals 0. And putting that into matrix form, we have 2 eigenvalues, and they're both 1. Finally, for the wave equation, we had utt equals c squared uxx. Oh, and a bit of a typo in the previous one. This should be an x and a y for my derivatives. So in this instance, we have 2 eigenvalues, again, one of them being 1 and one of them being -c squared. So flavor-wise, it doesn't matter what the magnitude of the eigenvalues are. What matters is the sign. And the thing that's making these things sort of distinguish between one another is the fact that in the heat equation, there's an eigenvalue with 0. In the Laplace equation, both the eigenvalues have the same sign. And in the wave equation, one of the eigenvalues has a different sign than another one. So other partial differential equations with those properties we'd expect to behave like the heat equation, the wave equation, or the Laplace equation specifically. And these equations define 3 different broad categories. We call equations that behave like the heat equation parabolic. Equations that behave like the Laplace equation are called elliptic. And last but not least, equations which behave like the wave equation are called hyperbolic. So this leads to the classical classification of second-order partial differential equations, which is traditionally attributed to Hadamard. Starting out, if at least one of the eigenvalues of the matrix is 0, we call the partial differential equation parabolic. If all the eigenvalues are non-zero and they all share the same sign, either they're all positive or they're all negative, it's called elliptic. If all the eigenvalues are non-zero and all but one have the same sign, so all of them are positive except for one negative one, or alternatively, all of them are negative except for one positive one, we call it hyperbolic. And in the last situation, when there's more than one which is negative and more than one which is positive, but they're all still non-zero, we call the PDE ultra hyperbolic. Now it's worth pointing out here that some authors for parabolic require also that the non-zero eigenvalues all have the same sign. Some authors don't, so there is a little bit of disagreement about this classification in some sense, but this at least is a pretty good place to start. So going back to one of the examples that we started with, uxx plus 3uyy minus 2uxy equals 0. We write this in our matrix form using the matrix 1, -1, -1, 3. Now to figure out if this is going to behave more like the heat equation, the Laplace equation, or the wave equation, I'm just going to try to figure out what the eigenvalues of this matrix are. And I do that the usual way. I'm going to take x times the identity matrix minus this matrix. So I'll call this matrix A. I'm going to do xi minus A, giving me the matrix x minus 1, 1, 1, x minus 3. And I take the determinant of this matrix, obtaining the polynomial x squared minus 4x plus 2. The roots of this polynomial are given by the quadratic formula as 2 plus or minus the square root of 2, both of which are positive. So both of the eigenvalues have the same size, are the same sign, and so I classify this differential equation as being elliptic. And indeed, with the right coordinate transformation, we can transform this into an identical copy of Laplace's equation. So we can solve this equation explicitly by converting it and then solving Laplace's equation like we've done before. That's all for now. Thanks for watching.